Optics, or the study of light, begins with Lecture 36 of Physics 72. The first part covers geometric optics, and this lecture focuses on the phenomena of reflection and refraction. As with any lesson dealing with new concepts, Lecture 36 has a handful of objectives. Don't worry, these are easy to introduce. You may pause the video to check all of the objectives. We ended electromagnetism by asserting that light is a form of an EM radiation. We have not considered studying light on its own, and this has been done way before the time of Maxwell, Ampere, and Gauss. They were just the ones who bridged light and electromagnetism. For this part, we're going to understand what light rays are and how they are related to wavefronts. Optics is the study of how light and other forms of EM waves behave. It tries to understand how these waves travel, why different colors of light travel different paths, and how else we can bend these waves to our advantage. It is one of the older studies in physics and remains to be a prevalent area of research today. Known studies about the nature of light go way back to the time of ancient Greece. It was thought then that light was made up of streams of particles called corpuscles emitted by light sources. Many have tried to measure the speed of light, but it was thought then to be too fast, and a lot were resigned to the fact that maybe its travel was instantaneous due to the limitations of their devices. Isaac Newton strengthened the light is a particle argument with his contributions to optics in the 17th century. Today, the light particles and the energy carriers are called photons. These photons are emitted whenever atoms go from a higher to a lower energy level. From energy conservation, the lost energy has to be converted to something, and that something is light energy. Sometimes the light that is already emitted re-enters these atoms, so now it goes from a lower to a higher energy, and we call this absorption of light. Now it turns out that the color of the light emitted depends on the amount of energy it carries. The discrete combinations of colors emitted is also unique to the atom or the molecule that released it, and this phenomenon is utilized in identifying or classifying unknown materials. The frequencies that define the colors emitted don't encompass the whole visible light spectrum and take on discrete values. More on this topic is actually expounded in quantum physics. The nature of light was, and is still currently, a much debated topic. The other side of the argument argues that light is actually a wave. The wave-like nature of light was favored by a lot of scientists in the 17th century, and this caused a lot of bitter rivalries, such as Newton and Hooke. Light as a wave had an enormous advantage in the advent of electromagnetic theory, which was championed by Maxwell and Hertz. Wave-like properties of light have already been revealed much in electromagnetic theory, where Maxwell's equations show that these waves travel at the speed of light in vacuum. We see that light travels like a wave in lasers, or even in everyday objects, such as how a mixture of colors in oil puddles is spread. At the time when light as a wave was winning the battle, Einstein made the fight more even with a paper that granted him a Nobel Prize. Hertz discovered that electrons from metals were emitted when hit with electromagnetic radiation. What was surprising was that the charges' kinetic energy, or their average velocities, released from the material did not change if you varied the intensity or the amplitude of the radiation. It was actually the frequency of the radiation emitted that governed the velocities of the charges released. This was something that cannot be explained by wave-like properties of light, but it is a reasonable conclusion if light were considered as particles called photons, and they are classified by different levels of energy based on their frequency. The debate was reignited with the photoelectric effect and was actually one of the sparks that brought quantum physics to life. At that point, the nature of light cannot be fully explained if we just treated it exclusively as a wave or a particle. This led the scientific community to consider that maybe light had a dual nature. Richard Feynman, in his work on quantum electrodynamics, posited that to reconcile the contradictory wave-like and particle-like properties of light, light must be considered to have both wave and particle properties. Understanding absorption and emission of light was best described by particle properties, but the propagation of light was best explained with wave models. A recent 2015 paper in Nature showed light with both wave and particle properties, as you can see on the left. The wave nature shown in the upper graph had clear crests and troughs. The particle behavior was revealed in the lower part of the graph, with the outlines grouping energy quantization. More about the property particles of light is studied in Physics 73. As we were just introduced to EM theory a couple of lessons ago, our focus is on understanding how light is propagated as a wave. The word wavefront was thrown around a couple of times in EM waves as the leading edge of a wave, but it was never explicitly defined. More generally, the wavefront is defined as the locus or the collection of all adjacent points at which the phase of vibration of a physical quantity associated with the wave is the same. A lot of words, but looking at this example of water ripples, the expanding circles are the wave crests or the amplitudes, and the sinks are the troughs. Both of them can be considered wavefronts because both, or if you look at just the crests, all of them have the same phase, right, at which the maximum value of the trig function occurs. The wavefronts of sound waves that spread from still air comes in the form of fronts of constant pressure. Waves that come from point sources emit spherical wavefronts that have the source as its center. These fronts can be pretty much everywhere when you draw them, so we usually only draw a few of them and then just imagine the rest. One can choose to draw a few crests, and the propagation of that wave can be clear. If you want to focus more on where these waves are going to, we can actually further simplify our diagrams by drawing rays instead of wavefronts. A ray can be used to represent the direction at which the wave travels. Looking at light in the particle viewpoint, the ray dictates the path of the photon. Spherical wavefronts can be replaced by rays originating from the sphere center or the source. Regardless what shape these wavefronts are, rays would always be perpendicular to wavefronts and are parallel to each other. If we're talking about just simple materials, you won't really see these wavefronts bend in weird directions. This means that in simple materials, we can expect the rays to always be straight. These simple materials are called isotropic media. These are media which have the same material properties if you look at it in the x, y, or z directions. These materials are homogeneous. As a guide for isotropy, you can imagine the appreciable force of gravity to be not isotropic or anisotropic because it only points vertically but not horizontally. With this, we accomplish our first objective in using concepts of wavefronts and rays to describe how waves travel in space. More on this in the future slides. The second part of Lecture 36 discusses reflection and refraction. We try to discover how light changes its direction when it crosses boundaries of different materials. In this part of the lecture, we use the ray model of light to explore two of the most common and important aspects of how light travels: reflection and refraction. As light crosses boundaries, it gets split to two rays, one that bounces back, or the reflected ray, and the other one passing through, the transmitted or refracted ray. The graphic on the right shows an example of both in action. We see a girl looking at a reflection of a hat that just flew away from her. Instead of looking at the hat itself, she is looking at the reflection of the hat from the window of Alice's coffee shop. Inside the coffee shop, the man on the right is also seeing the hat, but he is not seeing the hat at its exact location. The light travels from the hat, through the air, and crosses the glass boundary of the window before traveling back to the air inside the coffee shop. The rays have been refracted or bent through its path. Pinpointing how the light is reflected or how much its path is bent will be discussed in the next few slides. Before we begin, we must classify the different types of light rays present in the phenomena for reflection and refraction. The waves traveling outside and through the glass are represented by different rays. The light rays coming from the hat to before it hits the glass boundary are called incident rays, as shown here. The rays that bounce off the glass and eventually end up at the eyes of the woman are called refracted rays, or here. The bent rays that go through the boundary are called refracted rays. Note that this diagram is in 2D, even though light travels in 3D. To simplify the analysis of how these waves travel, We set all of these rays to lie on one plane, which we call the plane of incidence. You can imagine the plane of incidence to be the plane at which this figure is drawn. We can further simplify the representation by minimizing the number of rays drawn to 3, one for each unique ray. With this simplification, we can now define angles at which these rays strike or leave the boundary. These angles are measured from the line segment perpendicular to the boundary, which we will call the normal to the surface. This normal line also lies in the plane of incidence. How these light rays propagate are dictated by the material properties of the media at which they travel. Recall that electromagnetic waves travel at different speeds for various materials. It's c in vacuum and v for any other material, and their values are dictated by the material's permittivity and permeability. The ratio of wave speeds in vacuum to the wave speed in a material is called the index of refraction, n. You're dividing speed by speed, so n is a dimensionless constant, and since c is the fastest light can travel, n will be greater than or equal to 1. We note that light will always travel more slowly in a material than in vacuum. Refractive index n is the simplest physical property in classifying the medium at which light travels. Once the refractive index of the medium changes, we expect the light rays to deviate from a straight path. We first analyze reflection. We have our first material A with refractive index n sub A. This is where we'll have the original or incident ray come from. This is also where the reflected ray will travel. Material B with refractive index n sub B is where the refracted or transmitted ray will be, but we're not going to focus on that for now. The material boundary is where the incident ray will be reflected and refracted. The incident ray will make an angle theta I with a normal, and this will be our angle of incidence. Once the incident ray strikes the boundary, light will already change its path. Part of the ray will be reflected, and its direction will be indicated by the reflected ray. The angle it makes with the normal is called theta sub r, and is called the angle of reflection. Based on experiments done by ancient Greeks, namely Euclid, the law of reflection states that incident angle theta sub I and reflected angle theta sub r will always be equal. This is the law of reflection. With this, we accomplish our objective in predicting the direction of reflected light. We've ignored the refracted ray in the previous slide, so now we're going to give it the attention it deserves. While the conclusion of this law was discovered empirically way back, there is a mathematical derivation in chapter 33.7 of the book. However, this is outside the scope of Physics 72. We will still have the same materials, incident ray, boundary, and normal from the previous example, but we're going to change the name of the angle of incidence to theta sub A, as this is the angle the ray makes with respect to the normal for this material. Upon crossing the boundary, the transmitted ray gets bent. This ray makes an angle theta sub B with respect to the normal. We'll call this the refracted ray. The signs of the angles theta sub A and theta sub B are actually dictated by the material's refractive indices, and is given by the equation n sub A sine theta sub A is equal to n sub B sine theta sub B. This equation is called Snell's law, named after Dutch scientist Willebrord Snellius. While this relationship was earlier discovered in Persia, its connection with refractive index only came much later. Theta sub A and theta sub B are the angles of incidence and refraction respectively. These subscripts are assigned according to the material instead of their role, because you'll soon find out in answering problems with multiple boundaries that this angle is the same for the material regardless whether it's entering or leaving the boundary. With this, we accomplish our objective in predicting the direction of refracted light using Snell's law. How light is refracted depends on which of the refractive indices is actually higher. If the refracted ray is located in the material with a higher refractive index, where light travels slower, so in this case it would be n sub b, we end up with the refracted ray bending more towards the normal. This is explained by Snell's law. Isolating the refractive indices on one side and the signs on the other, we see that n sub b over n sub a has to be greater than 1 because we said n sub b is higher than n sub a. This also means that the ratio sine theta sub a over sine theta sub b is greater than 1. The relevant domain of angles for our setup is 0 to 90 degrees because beyond 90 degrees already extending on the other side. At this domain, the greater the angle, the greater the sine. This means that theta sub a has to be greater than theta sub b, or that the refracted ray will be closer to the normal than the incident ray. To reiterate, this only happens if the ray enters a material of larger refractive index. If we consider the opposite case, where the refractive index is actually smaller in the transmitted side, we see a different result. So for this case, n sub b has to be less than n sub a. The ratio n sub b over n sub a would then be less than 1, and the angle of refraction theta sub b would actually be larger than the incident angle theta sub a. This means that a ray entering a material of smaller refractive index would actually bend away from the normal. There is a special case wherein the incident light is normal, or theta sub a is equal to 0, and this results in the refracted ray not being bent at all. This can still make sense for Snell's law, because if theta sub a is 0, then the left-hand side of Snell's law is 0. But since refractive index n can never be less than 1, the equality only holds if sine theta sub b is 0 as well. And that can only happen when theta sub b is 0, which leads to the conclusion that the angle will not change at all. Common examples of how we see Snell's law in action are closer to your household than you think. It explains why the utensils or straws in glasses filled with water look bent. The picture on the right also shows lasers of different colors that get refracted upon entering water. One can even see the part where the green laser is reflected. Let's check our understanding of refraction with this scenario. Gone fishing with a spear. You are standing on the shore of the lake near the math building. You spot a fish swimming some distance below the lake's surface. If you want to spear the fish, where should you aim the spear? A. Above the apparent position. B. Below the apparent position. Or C. Directly where you see it. The answer for this exercise is that you should aim below the apparent position of the fish, or letter B. The question is, how did we arrive at this answer? This diagram shows why we aim lower. The observer will see the fish in its apparent position, but its location is actually different because of refraction. I'll go through the specifics in the next slide. Light coming from the fish will travel from water to air. So let's place the fish here. The incident ray travels through water, and the refracted ray travels through air. The refracted ray should end up at the observer's eye. Since light travels slower in water than in air, water's refractive index is higher than air's. From Snell's law, the refracted ray should be angled farther from the normal compared to the incident ray. Let's check the observer first. His line of sight will actually be a straight path from the refracted ray, and extending this ray to the water unbent points to where the observer will see the fish. We call this the apparent location of the fish, and is actually higher than the actual location. This is why the observer is asked to aim lower to spear the fish. We'll leave how much lower he needs to aim to his experience and intuition in fishing or his amazing grasp of optics. For the second question, we go with the same situation, but this time we'll just use a laser to pinpoint the fish instead of spearing it. This time, it's going to be light that's traveling instead of the wooden spear. How then should we aim the laser? While it may not seem obvious at first, we should actually just aim directly at the apparent position of the fish. Remember that the spear does not bend, so we aim below its apparent location. On the other hand, this laser will actually follow the same path as the light from the fish to the observer, because laser, well, is light. We just aim directly at the apparent position of the fish and let refraction do its work. We review that it is the wavelength of light that changes in different media and not frequency. So that means that frequency remains the same. So changes in wave speed v equals lambda f is due to the wavelengths changing. How this wavelength specifically changes is given by the equation lambda is equal to lambda naught over n, or n is the index of refraction. In seeing how wavelength changes with refractive index, we complete our objective in understanding how n affects wavelength, light rays, and the speed of light. We finally reach the last part of the lecture, which discusses the phenomenon of trapping light inside a material via total internal reflection. From the previous section, we know that light rays striking the boundary of two different materials get split to a reflected wave and a transmitted or refracted wave. The angle of the refracted ray depends on both the angle of incidence as well as the refractive indices of both materials involved. We then ask if it's possible to reflect all of the incident light, leaving none to be transmitted or refracted. Turns out that you can, with certain restrictions. First, we call this phenomenon total internal reflection, or TIR. So let's go through these restrictions. Firstly, TIR occurs only if light travels from a material of higher index to a material of lower index. In this case, our material on the left side, N sub A, has a higher refractive index than 1 in N sub B. So usually 1.52 is the refractive index of glass and 1.0 is the refractive index of vacuum or air. The second restriction is that TIR only starts happening at some critical angle. At this critical angle, the refracted ray will travel exactly at the boundary, which effectively leaves nothing for the other side to see. Another way of saying that the refracted ray will travel exactly at the boundary is when the angle of refraction is 90 degrees. Total internal reflection will happen if the angle of incidence is larger than or equal to a critical angle called theta sub crit. Rearranging Snell's law and setting theta sub b to 90 degrees leaves you with sine theta sub critical is equal to n sub b over n sub a. From this, we can calculate the critical angle by just getting the arcsine of n sub b over n sub a. We don't need to worry about the argument being greater than 1, because TIR only happens when the incident index NA is greater than NB. This graphic shows an example of TIR in real life. So the graphic's on the right, the diagram is on the left. Light is emitted in water by sources at different angles. One of the sources emits light that completely bounces back in the water, leaving none to be transmitted in air. So in this diagram, this would be the light that gets total internal reflection. Here are examples when lasers are used. Total internal reflection brings about a lot of applications, particularly when controlled emissions such as lasers are used. Some of these applications are already appreciated by households with fast internet and medical professionals that use advanced imaging apparatus. Endoscopes are tube-like instruments that are inserted directly to a human's orifices for direct imaging that is impossible for usual cameras. For the other application, information nowadays can also be transmitted via electromagnetic waves. Think of the crests as ones and minimum values as zeros in the binary language of computers. Higher frequencies mean more crests, and then that also means larger amounts of information. Back then, radio waves were the ones that can be transmitted at long distances without considerable losses. With fiber optics and TIR, we can just bounce visible light, which has higher frequencies than radio waves, through narrow cables to transmit big amounts of information at long distances. With this, we actually complete the objective of given n of different materials, we determine when total internal reflection occurs. Let's go through two examples to hone our understanding of reflection and refraction. So for this one, a fiber optic cable is composed of two materials, the cladding layer with an index of n sub clad, and the core material, which has an index of n sub core. If this cable is to be used, which of the following relationships between the indices of refraction be used in order to keep the light in the core? So here are your options. You may pause the video to check them. Remember that TIR can only happen if the incident material has a higher refractive index than the material where the wave is possibly transmitted. This means that the core should have a higher N than the cladding, and the cladding should have a higher N than air just in case some of the wave escapes the core. The answer should be B. For the second example, we have light is incident along the normal of a face of a glass prism of refractive index 1.52 as shown in the figure below. So the incident ray is going to hit the boundary AB. Now we're supposed to find the largest value that the angle A, which is this angle, can have without any light refracted out of the prism if the face, if A, the prism is immersed in air, and B, if the prism is immersed in water. I will leave understanding the solution up to you, but I will give the clue that no refracted ray will be present if total internal reflection happens. With a bit of geometry, we can get an expression for alpha based on the refractive indices. So if you're trying to solve the problem, it's going to hit it at this part. But then you have to draw the normal this way. So that means your angle should actually be this one. And then you're going to have your reflected ray, and then your reflected angle should be this one, and they should be the same. Another part that you have to consider is with geometry, this angle is also alpha. Here's the diagram and the solution to get the answer. You may pause the video if you wish. This is it for lecture 36. Thank you for listening.